What's up? This is Mario, and welcome to Awesome Acoustics. In this episode, we will talk about digital audio, starting with binary numbers and going over topics like sampling and aliasing. Digital audio has many advantages compared to analog media. It allows us to store a lot of audio in a small physical space. The audio can be copied and sent digitally. It is easier to process with filters and effects. We can analyze it and obtain a lot of information such as its frequency spectrum, and it is not affected by analog noise. An example of the latter is that noise was a common problem on analog TV and VHS. But nowadays, with digital video, noise is something we don't worry about. Like all physical phenomena, sound is considered analog or continuous. So, the only downside to digital audio is that it is made up of individual points, or in other words, discrete points. This is similar to how digital images are made up of discrete pixels. Converting something continuous to something made up of discrete points is known as discretization. By discretizing an analog wave, the digital wave will have empty spaces between the points. That is, part of the analog information is lost forever. When listening to the digital wave, this can be perceived as a loss of quality. However, with today's technology, we have audio resolution so fine that digital audio is indistinguishable from analog audio, and in most cases even clearer. Additionally, these days we have more digital storage space to store a lot of high-quality audio. To understand digital audio, it's important that we start with binary numbers. And to understand binary numbers, we should first analyze our decimal system. The decimal system is a numerical system where each digit can have one of 10 different values, hence the name decimal. If we go up in increments of 1, we eventually reach the maximum, in this case 9. And if we try to increase more, we have to go back to 0 and increase the next digit. Another way to interpret a decimal number is if we multiply each digit by a power of 10. 10 to the power of 0 is 1, 10 to the power of 1 is 10, 10 squared is 100, etc. Each digit is multiplied by its respective 10 to the power of n, and if we sum the resulting values, we get the full number. This may seem redundant, but it will be super helpful when we move to binary numbers. Now, binary numbers are called this way because each digit can have one of only two different values, 0 and 1. Also, these are the only numbers that are the same in decimal and in binary. Each increment in one system will correspond to an increment in the other system. Here, we have already reached the maximum, so our only option to continue advancing is to return to 0 and increase the next digit. Then, 2 in decimal would be 1 0 in binary. With one more increment, we would have 3 in decimal, which would be 1 1 in binary. If we now have two digits with their maximum value and we make another increment, these two digits return to 0 and we increment the third digit. So, 4 in decimal would be 1 0 0 in binary. At this point, it is easy to understand that 5 in decimal would be 1 0 1 in binary. With 3 digits, we can count from 0 to 7, which would be 8 numbers. While with 4 digits, we can count from 0 to 15, which is 16 numbers. That is, our numerical range doubles with each digit. But what happens when we have a huge binary number like this? It's probably too much work to count one by one, especially if we're not that familiar with binary. Let's remember how in decimal we multiplied each digit by a power of 10. Here we can do the same, but with powers of 2. Starting with a simpler example, let's remember that 101 in binary was 5 in decimal. 2 to the power of 0 is 1, 2 to the power of 1 is 2, and 2 squared is 4. Multiplying 101 by 4, 2, and 1 gives us 4 plus 0 plus 1, which equals 5. So, for a number like this, it's easier to use the method with the powers of 2. Of course, there are internet sites and calculators which you can use to convert between decimal and binary, but at least now we understand the logic behind the conversions. Now, a few moments ago, I mentioned converting an analog wave to a digital wave. Although the mathematical process of doing this is called discretization, the physical process of doing this is called sampling. Sampling consists of reading and storing the instantaneous amplitude of an analog wave at regular intervals of time. This creates samples. Sampling is a necessary process so that a computer or cell phone is able to work with a wave. This is because these devices can only handle digital information, so they cannot work with an analog wave. Sampling is carried out by a type of circuit or chip called an analog-to-digital converter, or ADC. Any cell phone or computer sound card must have one of these converters to read the electrical signal coming from the microphone, convert it to a digital wave, and send it to the processor. The time interval between two consecutive samples is called the sampling period. Then, if we divide 1 over the sampling period, we obtain the sampling frequency or sampling rate, which is measured in hertz. Remembering that hertz means repetitions per second, this means that the sampling rate in hertz tells us how many samples are taken in 1 second. Two standard sampling rates used in audio are 44.1 kHz and 48 kHz. This means that 44,100 samples or 48,000 samples are taken in 1 second, respectively. 44.1 kHz is the sampling rate used in CDs. Remember in episode 1 where I mentioned that the hertz were used for any repetitive event and not only waves? This is the main reason why I wanted to clarify it from the beginning, because sampling frequency in hertz expresses cycles of sampling, not cycles of a wave. Once you have your sampled wave, the points are typically joined with straight lines. This is simply to be able to visualize them. There is actually no information between the points. If your sampling rate is too low, you may have a problem called aliasing. Let's say we want to convert this wave from analog to digital, and we sample it like this. By connecting the dots, the samples are going to produce this, which looks like a sine wave with a different frequency than the original. That is, the digital wave has a different frequency than the analog wave we tried to measure. When this happens, the original wave cannot be recovered, so we would have to re-record it with a higher sampling rate. Therefore, it is important to avoid this from the beginning. This is a graph showing the frequencies of the original wave and the reconstructed wave. For simplicity, we will say that our sampling rate is 1000 Hz. Ideally, we would want this graph to be a diagonal line. That is, that the reconstructed frequency is always equal to the original frequency. In a certain range, this is going to be fulfilled. Here, it would be from the beginning up to 500 Hz. After that, if we keep increasing the frequency of the original wave, we will start to reconstruct lower frequencies. This means that we are not getting the correct information. After 1000 Hz, the reconstructed frequency starts to rise again, but it is well below the frequency it should have been. An interesting case is when we have an original frequency of 1000 Hz and a sampling frequency of 1000 Hz, which gives us a reconstructed frequency of 0 Hz. When the original frequency and the sampling frequency are equal, we will be taking exactly 1 sample per cycle. So, we would be reconstructing a horizontal line, which is considered a frequency of 0 Hz. In the case of having an original frequency of 500 Hz and a sampling frequency of 1000 Hz, we would be taking exactly 2 samples per cycle, which gives us a triangle wave. Although it is true that it is a different waveform than the original, at least it still has the correct frequency. So, with a sampling rate of 1000 Hz, 500 Hz is the maximum frequency that we can sample without aliasing. Another example with this sampling rate is that if we try to sample a 700 Hz wave, we will get a 300 Hz digital wave. This would look like the first visual example I showed. In this region, there is another way in which we can visualize aliasing. It's as if the original frequency reflected around 500 Hz, which here gives us the 300 Hz. We can describe all of this behavior more generally if we replace the frequencies by factors of the sampling frequency. So, we can see that the only range where we can reconstruct the correct frequencies is from 0 Hz to half of our sampling rate. And after that, we have aliasing. This important fact is known as the Nyquist theorem. and the frequency equal to half the sampling frequency is known as the Nyquist frequency, which will be different depending on the sampling frequency. Now, let's recall that the human audible range goes up to, at most, 20 kHz. Therefore, the minimum sampling rate needed to cover the human audible range without aliasing is 40 kHz. This is why 44.1 kHz and 48 kHz are standard sampling rates, because they are just above 40 kHz. When you have a digital wave and you finally want to play it, it has to be sent to a digital to analog converter, or DAC. This converter will produce the electrical signal that goes to your loudspeakers or headphones. Notice how we have a continuous wave again. The way the continuous wave is generated will depend on the quality of the DAC. Let's compare what an audio sounds like with different sampling rates. I will use 44 kHz, 22 kHz, 11 kHz, and 8 kHz. As we lower the sampling rate, the audio becomes more muffled. This is because we are losing the high frequencies. For digital signal processing applications, a sampling rate of at least 4 times the maximum frequency in the signal is typically recommended, while a sampling rate greater than 10 times the maximum frequency in the signal is considered oversampling. That is, an excessive use of digital data without considerable benefit. But for music, whether it's listening or producing, the standard 44.1 kHz and 48 kHz sampling rates are sufficient. At these sampling rates, frequencies close to 20 kHz might not appear reliable. For example, this is an 18 kHz wave sampled at 44.1 kHz. However, a DAC for audio is not going to produce this waveform exactly, but rather it smooths out the high frequencies and produces something more like a sine wave. For the low and middle frequencies, it is more important that the digital wave resembles what we want to reproduce. Although some audio engineers use a 96 kHz sampling rate, it can be a little excessive. There is currently no consensus on whether a significant improvement in audio quality can be perceived at 96 kHz. 192 kHz is sometimes mentioned as well, but this is definitely excessive. Additionally, with these sampling rates, audio files take up considerably more storage space, and in some cases, they can be too heavy to process. Personally, I always work with a sampling frequency of 48 kHz. So far, we have talked about how a wave is discretized in time, but there is also discretization of amplitude. Digital information can only be represented by digits, hence its name, and each digit is called a bit. If we had 3 bits to represent the instantaneous amplitudes of a wave, we would have up to 8 different possible binary numbers. That is, we can represent up to 8 discrete levels of amplitude. Here, we will need a level in the middle so that it is the zero of the digital range. Since we have an even number of levels, our zero can be either of these two. So for now, I will choose the 5th level. But also, waves are symmetrical around 0. So, having the maximum amplitude before clipping, we would typically be using 7 of these 8 levels. As a reminder, clipping is when a wave gets cut off due to exceeding the digital range, which I explained in episode 2. Here, I am arranging the binary numbers in ascending order. But computers typically arrange it in this way, called 2's complement, which is an alternate way of ordering the binary numbers. This will be invisible to a user who is strictly editing and recording audio, so there is little point in looking at it in detail. For simplicity, I will continue to display the numbers in ascending order. If we now had 4 bits, then we have 16 possible levels, of which we would typically use up to 15 due to the symmetry of the waves. This is what a 4-bit audio looks like, and we can clearly see the discrete instantaneous amplitudes. The number of bits that we have to represent instantaneous amplitudes is called bit depth, and each time we add a bit, we double the number of discrete levels, due to how binary numbers work. To find the number of possible discrete values from the bit depth, we raise 2 to the power of the bit depth. For example, 2 cubed is 8, and 2 to the power of 4 is 16. Let's listen to what an audio sounds like with depths of 16 bits, 5 bits, 4 bits, and 3 bits. Here, the first leap is very large, because the quality degradation is easy to perceive until down to 5 bits. So, as we lower the bit depth, the background noise increases. Specifically, this type of noise is called quantization noise, and it is caused by the low precision of the wave. This problem is more noticeable in audio sections with low amplitudes. 16 bits is enough for good quality audio, that is, without noticeable quantization noise. But during the production stage, it is recommended to use at least 24 bits, so that the audio can be processed with less distortion and noise. Together, the sampling rate and the bit depth create a grid, which shows all possible points where samples can be placed. The denser this grid, the more accurately we can reconstruct a wave. If we increase the sampling rate, we increase the horizontal density. And if we increase the bit depth, we increase the vertical density. This way of representing a digital signal is called pulse code modulation, or PCM, which is how a signal is stored in a WAV file. The bit rate is the number of bits in a full second of audio. For a WAV file, the bit rate would simply be the multiplication of the sampling rate, the bit depth, and the number of channels. That is, for stereo audio, we would add a multiplication by 2. For example, here we have 10 samples in 1 second. That is a sampling rate of 10 Hz. If the samples have a depth of 3 bits, then we would have a bit rate of 30 bits per second. If we manually count the number of bits in the image, we can confirm that they are 30. A more realistic example would be a WAV file with a sampling rate of 48 kHz, depth of 16 bits, and 2 channels, which would then have a bitrate of 1536 kilobits per second. Now, let's try to calculate the storage space of a WAV file, knowing only its specifications. Here I have a 4-second audio with the same sampling rate and bit depth, but only one channel, which gives 768 kilobits per second. And since the audio is 4 seconds, in total it would be 3072 kilobits, regardless of the audio it contains, even if it's pure silence. 3072 kilobits would be 3,072,000 bits. Then, 8 bits are 1 byte, so 3,072,000 bits would be 384,000 bytes. An important clarification is that although kilo in the metric system means 1000, a kilobyte would be 1024 bytes. For digital data, the factor of 1024 is common, since it is a power of 2. In the same way, 1 megabyte is 1024 kilobytes, and 1 gigabyte is 1024 megabytes. So, if we divide 384,000 by 1024 to convert from bytes to kilobytes, this should give us the exact size in kilobytes. This equals 375 kilobytes. Now, let's look at our 4-second WAV file. And its size is exactly 375 kilobytes. Notice that this WAV format mentions 16 bits and PCM. This means that this format has 65,536 possible levels of instantaneous amplitude. Compressed audio formats, such as MP3, store information in a much more complex way. Explaining the MP3 compression process would take me a whole episode, and for now it is too advanced a topic, so for the moment we will not look into it in detail. What we can observe is the bitrate. We can find this by right-clicking on the file, going to Properties, and then going to the Details tab. However, for MP3, this is more like an average bitrate, since the MP3 format can have a variable bitrate throughout the file. Let's listen to MP3 files with different bitrates. I will use 256, 128, 96, and 64 kilobits per second. Although 256 is pretty standard for high-quality MP3, even down to 128 it's still hard to notice a degradation of quality. But as soon as we go below 128, the degradation becomes obvious. For MP3, I would personally recommend bitrates of 192 or higher, and to never use less than 128. In general, MP3 achieves a quality comparable to WAV format with a file size around 5 times smaller. Now, I want to show you something regarding the NES waveforms. If we look at the triangle wave of the Zelda music from the first episode, we can see discrete increments here. If we count them, we can see that they are 16. This means that the bit depth of the NES music is 4 bits. Music that uses NES sounds is sometimes called 8-bit, because the NES in general is an 8-bit system. But here we can see that the music itself is technically 4 bits. A more accurate way to call this kind of music is simply chiptune. The levels don't look perfectly horizontal, most likely due to the quality of the DAC. That is, what we are looking at is not the actual digital wave, but after it has been converted to analog. Earlier I mentioned that considering a level at 0 and symmetric waves, we would typically leave one level unused. But here it is preferable to take advantage of all the available levels, since discarding one level out of only 16 would be a big loss of range. In the first episode, I mentioned that the NES has 4 channels with predetermined waveforms, and on these channels the waves are generated directly by the NES. However, it also has a 5th channel for sampled waves, that is, arbitrary waveforms that are stored inside the cartridge. This 5th channel does have a depth of 8 bits. But it was rarely used because the sampled waves took up a lot of storage space in the cartridge. An example where it was used is for the percussions in the music of Super Mario Bros. 3. I will leave the link to the animation in the description. With that, we conclude this episode, and in the next one, we will talk about audio editing in the Audacity software. See you!